Let's recall that a sufficiently smooth function f of x can be represented by a Taylor series in the following way. We can develop it around the point x0, and this means the nth derivative of f at the point x0. And so this nth derivative is multiplied with x minus x0 in the power of n and multiplied with the faculty of n. And the summation is taken from n equal to 0 to infinity. So if we now replace x here by x plus h and replace x0 by x, then we obtain the following. We get x plus h equal to this in the power of n. And then we can, this is done just to remove x. So x0 was replaced by x, so we of course get this expression. Removing x, we obtain this simple relation. Just let's write some of these terms. The first term is when n is equal to 0. Then we have the 0th derivative of f, which is the same as f itself. And h is in the power of 0 when h in 0 is the same as 1. And 0 faculty is the same as 1. So therefore we get this term when n is equal to 0. When n is equal to 1, we obtain this term, and when n is equal to 2, we get this term, and we also take the last term here when n is equal to 3. Of course, we get infinitely many other terms as well, but let us just focus on these small terms first. We can now find a difference equation for the Poissons equation. The Poissons equation takes this form, and now if we write u equal to u of x, y, and let y be a fixed number, then we can differentiate this with respect to x. Instead of using f of x, which we have done earlier in this series, we now replace it by uxy. And replacing it, we certainly get this series. We only have these 4 first terms of the series. So in fact it should be approximately equal to this, not equal. And the same way when x is, if we replace h by minus h, we get this series. In order to see this, just replace h in this equation by minus h. Then you see that the minus h in the square of minus h is of course the same as h square. And minus h in 3 is the same as minus 8, what we have written here. So if we just subtract these two equations, we easily find that this subtraction is equal to 2h, the derivative of u with respect to x, plus this term. So subtracting these two equations, we obtain this equation. So we have this difference equal to 2 times h times the derivative of u with respect to x, plus some higher ordered terms of h. And these terms are approximately equal to 0 when h is small, because, for example, h in the power of 3 is a very small value when h is a small value. So compared with this, it's almost like nothing. So therefore, we can make this approximation. Dividing both sides with 2h, we obtain that the derivative of u with respect to x is approximately equal to this guy. In the same manner, we can, by adding these two equations, we can obtain that the derivative, the second derivative of u with respect to x is equal to 1 over h squared multiplied with this expression. And of course, this is just when h is a small value, because then we get these higher order terms are very much smaller. Let's we can do exactly the same, keeping x. If you know, keep x a fixed value, we can make a Taylor expansion of this function with respect to the second variable. And if we, instead of using h, use the constant k instead, we obtain in exactly the same way as above this development, Taylor development of this function. And replacing k here by minus k, we obtain this. This is exactly as above. So, and we obtain these two expressions. Note now that if we have some coordinate x, y in the middle here, then the coordinate x, y plus k, must be up here. So the difference between these two values in the vertical direction is equal to k, and the space between these 2 points is equal to h, the same here, and the space between this middle point and the point here is also k. So here are the coordinates of these 5 points. Note that if we are standing here, then this point is in direction north of this point. So therefore we index it by capital N. This point is east of this middle point, so we index it capital E. And this is the west point, and this is the south point. So if we just now use the Poisson equation, which is we recall that the Poisson equation takes this form, then we can use our approximation of uxx and our approximation of uyy and add these two together, and we obtain this equation. So in fact here we have just multiplied with h squared on both sides. And note that in the case when this f on the right side is equal to 0, then we obtain the Laplace equation. And in this case this equation turns into this simple equation. If we now use instead of using this coordinate, call this coordinate the east coordinate. Just see here, this is the east coordinate, north coordinate, west coordinate, south coordinate. It's easier for us to remember what we are doing. So then we can call this u of capital E the east coordinate, and this is u of capital N, which is the north coordinate, and this is the west coordinate, and in fact, yes, and this is the south coordinate. So it's equal to this should be equal to 0, and then if for the Laplace equation, but for the Poisson equation it's h squared multiplied with this f. So doing this substitution, we get this equation. So we are in a position xy, and we have some coordinate on the north, east, west, and south of this coordinate. So let me just add that in this special case, in order to get this equation, I forgot to remember this, we have to put h equal to k. Otherwise we get another equation. So if we consider the coefficients on u, e, un, uv, us, and the middle, the u in the middle point, then we obtain that on all these four coefficients is equal to 0, and this coefficient is equal to -4. So if we are standing, this is visually easy to remember. If we are standing in the middle point, we should multiply with -4, and standing in the north, we should multiply it with 1, in the east with 1, south with 1, and west with 1. So maybe this way of writing the equation could be easier for us. So in symbolic form we can write the equation by this. We just use this symbol and multiply it in some sense with u, and get h squared multiplied with f of x, y. The Dirichlet problem will be solved very soon by using numerical methods where we use this scheme.